The Dirac Delta function that can be approximated by a sequence of functions. Okay, delta nx where n tends to infinity. Okay, so the Dirac delta function can be approximated by the sequence of functions delta nx where this n goes to infinity. The first one is the first one, delta nx is 0 for x less than minus 1 by 2n. Okay, this one, and it is equal to n for x in between minus 1 by 2n and 1 by 2n, and it is equal to 0 for x greater than 1 by 2n. So graphically it can be written or it can be represented in this form. See, the x or the delta nx is n for x in between minus 1 by 2n and 1 by 2n. Okay, and it is 0 for x greater than 1 by 2n and less than 1 by 2n in this region. Okay, and we can see the height of this is height of is this function is n, height n, and what about the width? Width is 1 by n, minus 1 by 2n 2 plus 1 by 2n, so width is 1 by n. So area is equal to n into 1 by n, that is equal to 1. So the area of this rectangular portion is 1. So this one is clearly representing a delta function as n tends to infinity. As n tends to infinity, the height tends to infinity and the width tends to 0, so narrow width. So as we define the property of the Dirac delta function, the height at x tends to 0, height tends to infinity, the height of the function, and width tends to 0. The area is 1 unity. So this one clearly, this is clearly representing the Dirac delta function, or this is an approximation of the Dirac delta function. Okay. The second one is delta nx equal to this n root pi exponential minus n square x square. Okay. So this one mathematically, when x equal to 0, here when x equal to 0, its value is n over root pi, and as n tends to infinity, this will become infinite. Okay, this will become infinite, and its area can be shown to be equal to 1, and for x much greater than 0, its value is 0. Okay, its value is 0 because of the as x tends to very large values, this will become 0, tend to a small value. So that is shown here. So this is delta nx. So this one shows, or it is an approximation of the Dirac delta function. The second one is this. Oh, sorry, the third one is this. Okay. The third one, this is also an approximation of the Dirac delta function. We can show that as n tends to infinity, this will approximate to the Dirac delta function. The fourth one, which is more commonly used, is this, the delta nx equal to sin nx by pi x. As n tends to infinity, this will represent the Dirac delta function. So sin nx by pi x, sin nx by pi x is this. Let's examine the behavior of this function for small x, that is the limit as x tends to 0. We are examining this function sin nx by pi x as n tends to infinity for small x, okay, or that is the limit as x tends to 0. So we will be getting limit x tends to 0 sin nx by pi x, that is equal to n by pi. Okay, L'Hospital's rule, when you apply sin nx by pi x, that will be equal to n by pi. On the numerator you will get cos nx, and the denominator you will get pi, and when you put x equal to 0 you will get n by pi. And since n is there in the numerator, as n tends to infinity, you see the amplitude goes to infinity, the amplitude goes to infinite at the singularity at x equal to 0. So this amplitude, this will go to infinity. Okay, this will go to infinity as n tends to infinity. And for mod x, for large mod x, so that means the value of x very large, sin nx by pi x, that oscillates, sin nx actually will be oscillating with period 2 pi by n. Okay, because sin x is an oscillatory function with period 2 pi. So sin nx, that will be oscillating with period 2 pi by n. Okay, and the amplitude, and its amplitude falls as 1 by mod x, because x is present in the denominator. So amplitude falls as 1 by mod x. We are using mod x, the magnitude of x, because we consider x positive as well as x negative. Okay, so that's why we are taking 1 by mod x here. So our function, this thing, as x tends to infinity and as x tends to minus infinity, x very large, its amplitude decreases, and as n tends to infinity, the period 2 pi by n, this will tend to 0. That means you will be actually getting the function like this. Okay, so the limit as n tends to infinity, the limit as n tends to infinity, the period gets infinitesimally narrow, so that the function approaches 0 everywhere except for the infinite spike that we are going to get, which is infinitely small width. This width will be very small, okay, at the singularity. So this function is clearly representing the Dirac delta function. Okay. Now we can show the area for the Dirac delta function. We know the area delta x ds is equal to 1. Okay, that we can get here. Okay, see, limit minus infinity to plus infinity sin nx by pi x dx, that is equal to limit n tends to infinity 2 times 0 to infinity sin nx by x. So we are changing the limit from minus infinity to plus infinity to 0 to infinity. Okay, 0 to infinity. So you have 2 here. Then this is equal to 2 by pi into pi by 2, that is equal to 1. because we are using this standard integral value, integral 0 to infinity sin nx by x is equal to pi by 2. That's a standard integral. We need some special methods to solve this, to evaluate this integral. Its value is pi by 2. The interesting thing is this is independent of n. Okay, it does not depend on n. So that its value is pi by 2. So we are getting this as equal to 1. So we get the second integral like this. Then integral, so we have got the area is equal to 1. Now we see an integral representation of the delta function. It is this delta x equal to 1 by 2 pi integral minus infinity to plus infinity exponential I kx dk. This is an integral representation of the delta function. We just proved that we start with minus infinity to plus infinity exponential I kx dk. That is equal to limit n tends to infinity integral minus n to plus n, n tends to infinity, okay, exponential I kx dk. As we integrate, you will get this exponential I kx by ix limits minus n to plus n. So see, the integration is with respect to k. So this is limit n tends to infinity I kn minus exponential minus exponential ixn minus exponential minus ixn by ix. Okay, so this is equal to 2 pi limit n tends to infinity ixn minus I exponential minus ixn by 2I pi x. So this is 2 pi limit n tends to infinity. This thing is, we know, sin xn. That is the formula for sin xn. So sin xn by pi x we get, which is, this thing is, as we know, this thing is the limit n tends to infinity sin xn by pi x is 2 pi delta x. Sorry, this is the delta x. So we have this 2 pi delta x. So we started from where minus infinity to plus infinity exponential I kx dk, and we got what? 2 pi delta x. So one can say, right, delta x is equal to 1 by 2 pi. Delta x is 1 by 2 pi minus infinity to plus infinity exponential I kx dk. Now separating the real and imaginary parts, we know we can write exponential I kx as cos kx plus I sin kx. So we get 1 by 2 pi minus infinity to plus infinity cos kx dk. This is equal to delta k. This is for the real part and for the real part. And for the imaginary part, you will get minus infinity to plus infinity sin kx dk, that is equal to 0. And this is the most commonly used as an, this equation A is most commonly used as an explicit expression for the Dirac delta function. Okay.